Lean 6, Sigma, GB, and BB, identification of factors, potential X's. Certainly. Below is an enhanced and detailed training content module on identification of factors, potential X's, for Lean 6 Sigma Green Belt, LSSGB, and Black Belt, LSSBB programs, including richer explanations, layered examples, tool comparisons, and learning pathways. Module Context. This module is part of the Analyze phase in the DMAIC methodology. The main goal here is to identify which process inputs, also called X's, have a significant impact on the process output, or Y. By understanding which inputs affect the output the most, we can focus on controlling these critical factors to improve the overall process performance. This helps in making data-driven decisions and ensures that the improvements are sustainable. Learning objectives. Participants will be able to understand the mathematical relationship between inputs and outputs, y equals f of x, systematically identify potential XS's using qualitative and quantitative tools, prioritize and validate X's using process knowledge and data. Apply these tools across manufacturing and services through real-life scenarios. Understanding the y equals f of x equation. In Lean Six Sigma, we focus on improving processes by understanding the relationship between outputs and inputs. Y represents the output, the result we want to improve. X1, X2, X3, Xn represent the inputs, the variables that affect or influence Y. Let's look at some examples across different industries. In healthcare, if we want to reduce patient wait time, we need to look at inputs like registration time, lab result delays, and doctor availability. In the BPO industry, to improve call resolution time, we focus on inputs like agent knowledge, call routing, and script design. In manufacturing, if we aim to reduce product defects, key inputs include tools for identification of potential excesses, process, mapping, SIPOC, and value stream. Mapping helps us break a process into logical steps. This lets us identify where delays, errors, or handoffs happen. We use these tools when we want to understand the process flow and find out where variation or problems might enter. For example, in a claims process, a value stream map showed excessive looping during the medical review step. Possible causes include reviewer workload, unclear decision criteria, or lack of digitization slowing the process. The fishbone diagram, also called the cause and effect diagram, helps us organize brainstormed causes of a problem into categories. Typical categories include man, machine, method, material, measurement, and environment. We use this tool when multiple teams or departments contribute to the problem, so we can clearly see all possible causes. For example, causes might be reagent lot expiry under material, non-standardized sampling method under method, or lab system calibration errors under measurement. The 5 Whys analysis helps us dig deeper from a problem symptom to the root cause by repeatedly asking why. We use this method when a simple linear root cause analysis is suitable. For example, problem: patient discharge is delayed. Why? Final consultation delayed. Why? Doctor not available. Why? No standard scheduling. Why? No dedicated discharge planner. Why? No role defined in the SOP. Potential causes might include lack of role clarity or absence of a scheduling tool. Failure modes and effects. Analysis, or FMEA, is a structured tool to identify potential failure points in a process and assess their impact. It scores each failure on severity, occurrence, and detection to calculate a risk priority number, or RPN. We use FMEA when we need to prioritize risks in complex processes that have multiple steps or components. For example, in a car seat assembly line. Failure, incorrect bolt torque. Cause, X, tool not calibrated, RPN. High risk. Critical causes identified include the calibration schedule and operator checklist compliance. The cause and effect matrix links process inputs to critical to quality outputs, or CTQs. Inputs are scored based on their impact on the CTQs, helping prioritize focus areas. We use this tool when CTQs are already identified, and we need to understand which inputs, XS, most affect them. For example, in a software QA process, CTQ, bug detection efficiency. Inputs, test case coverage, tester experience, test environment stability. The highest scoring input becomes the main focus for improvement. 6. Stratification and data segmentation. Stratification and data segmentation means dividing data by categories such as time, location, shift, operator, or product type. This helps us observe patterns and differences in performance based on context. We use this method when we suspect that performance varies in different situations or groups. For example, in a call center, error rates might be higher on weekends. Possible causes could be part-time agents working, lower supervision, or reduced technical support. 7th Pareto chart. A Pareto chart applies the 80-20 principle, showing that a few inputs or causes are responsible for most defects or delays. We use this when we have frequency or count data to identify the major contributors. For example, analyzing complaints might reveal that just 3 out of 20 reasons cause 75% of issues. These top causes should be the focus for improvement. 8. Regression analysis. Black belt level. Regression analysis helps us quantify the relationship between independent variables, called X-axis, and a dependent variable, called Y. We use this method when we have numerical data and want to understand how strongly each input influences the outcome. For example, predicting delivery delays, Y, based on factors like number of stops, route complexity, and driver experience, X-axis. 9. Design of experiments, DOE, black belt level. Design of experiments, or DOE, involves conducting controlled experiments to test the impact of multiple factors, or X's, at the same time. We use DOE when we can actively manipulate inputs to see how they affect the output. For example, optimizing print quality on a packaging line by experimenting with temperature, pressure, and ink type. Summary of tools. This slide presents key Lean Six Sigma tools and how they are used depending on the level of belt certification, either Green Belt, GB, or Black Belt, BB. SIPOC/VSM is used for visualizing the process from start to finish, great for identifying where inefficiencies may occur. Fishbone diagram is helpful for brainstorming potential causes of a problem. It's a structured way to look at root causes. 5 Whys allows teams to drill down to the root cause by repeatedly asking why until the true issue is uncovered. FMEA stands for Failure Modes and Effects Analysis. This is used for risk-based prioritization, especially in processes with many potential failure points. The cause and effect matrix helps in linking the inputs, X-is, to the critical outputs, CTQs, used mainly by black belts. Stratification is used to identify patterns within data. For example, how performance varies by time, location, or customer group. Pareto analysis helps in prioritizing top contributors based on the 80-20 principle. It helps you focus on the most impactful factors. Regression analysis is a statistical tool to quantify the impact of one or more variables on an output. This is black belt level. DOE, Design of experiments is used to validate combinations of inputs, very powerful for identifying optimal process settings, also for black belts. This table helps you decide which tools are appropriate at which belt level and for what type of problem-solving scenario. X validation pathway. Once potential X's are identified, collect data on each X to understand their behavior. Use graphical analysis tools like box plots, scatter plots, and time series charts to visualize patterns. Conduct hypothesis testing, such as t-tests, ANOVA, or chi-square tests to check for statistically significant differences. Apply regression models if the outcome variable y is numerical to quantify relationships. Finally, narrow the list down to a few critical X's that have the most impact and are controllable. This process helps focus improvement efforts effectively. Real-life cross-industry examples. Manufacturing. Example. Problem. Surface defects in coated sheet metal, Y. Percentage of defective sheets. Potential XS. Line speed, coater pressure, ambient humidity, operator-validated XS. High humidity and coater pressure were confirmed as key factors affecting defects. Service example. Problem. Delays in customer onboarding, Y. Onboarding lead time. Potential X's, CRM system delays, KYC documentation issues, customer responsiveness. Validated XS, system delays and unclear KYC checklist were identified as critical causes. Retail. Example. Problem. Order fulfillment errors, Y. Percentage of wrong items shipped. Potential X's, SKU similarity, picker fatigue, lighting conditions. Validated X's. Human error during the night shift was found to be the main cause. Key takeaways. Identification of X's bridges the gap between symptoms and root causes. Using a blend of team-based tools like Fishbone and 5Whys, along with data-driven methods like regression and FMEA, is the most effective approach. Validating the X's is critical before moving on to solutions. This is the heart of the analyze phase. Get this right, and the improve phase becomes much easier and more focused. Would you like me to transform this content into a slide deck with speaker notes, exercises or real-world case scenarios, multiple-choice questions and quizzes? Please let me know how you'd like to structure it for your training.